There are places in the universe where nothing happens. Not in the dramatic sense, not in the way stars explode or galaxies collide, but in the most absolute way imaginable. Nothing exists. Astronomers call these regions cosmic voids, vast expanses of space where galaxies are rare, matter is scarce, and even light feels reluctant to travel. They are not small. A single void can stretch for hundreds of millions of light years, large enough to swallow entire galaxy clusters without leaving a trace. Recently, the James Webb Space Telescope turned its gaze toward one of the largest voids ever mapped, not to find something, but to study almost nothing. And yet, even nothing has structure. According to our best cosmological models, the universe is woven like a web. Filaments of dark matter and galaxies stretching across unimaginable distances, intersecting, forming clusters, and between them, these voids. They are not perfectly empty. A few lonely galaxies drift there, isolated, cut off from the gravitational conversations of the cosmos. No nearby neighbors, no frequent mergers, no cosmic noise. Inside a void, time feels different, not because it changes, but because so little happens to measure it. A galaxy in a dense cluster evolves rapidly, pulled, distorted, ignited by interactions. But in a void, a galaxy can remain almost unchanged for billions of years. It simply exists. James Webb's instruments, designed to detect the faintest infrared signals, began collecting light that had traveled for billions of years across one of the emptiest regions ever observed. And what it found was not silence, but something far more unsettling. A pattern, barely there, yet impossible to ignore. In the deepest voids of the universe, absence is never complete. Even where matter is scarce, gravity still lingers. Invisible, patient, shaping what little remains. The James Webb Space Telescope, tuned to detect the faint glow of ancient light, began resolving structures where, for decades, we expected almost none. Not galaxies in abundance, not clusters, but something far more subtle. Thin, diffuse traces of hydrogen gas, so faint they barely register against the cosmic background. This gas is not random. It follows delicate patterns, guided by the underlying scaffolding of dark matter. According to the standard model of cosmology, dark matter forms the backbone of the universe, an unseen framework where gravity gathers ordinary matter into filaments and nodes. Even in voids, this framework does not disappear. It weakens, stretches, but never fully lets go. What Webb observed was a whisper of this structure, a nearly invisible lattice threading through emptiness. And within these faint threads, a handful of galaxies, isolated, undisturbed. Unlike galaxies in crowded regions, these have lived quiet lives. No violent mergers, no tidal distortions. Their stars burn slowly, their shapes remain pristine, almost ancient in their stillness. But something about them was unusual. Their distribution too aligned, their positions too precise. Not random, as one might expect in such emptiness. Instead, they traced the faint filaments with an eerie accuracy, as if, even in the largest void, the universe still follows rules, too subtle for us to fully understand. This is not unexpected, in theory. Simulations of large-scale structure predict that voids are not empty bubbles, but regions of low density, shaped by the same gravitational laws. And yet, seeing it so clearly in such an extreme environment changes something. Because here, stripped of cosmic noise, we are no longer observing complexity. We are observing the universe at its simplest. And sometimes, simplicity reveals patterns we were never meant to notice so easily. In the vast emptiness of a cosmic void, something subtle is always happening. Expansion. Not the kind you can feel, but the quiet stretching of space itself. The universe, since the moment of the Big Bang, has been expanding. Galaxies drift apart, distances grow, and over billions of years, this motion accelerates, driven by what we call dark energy, an unknown force making the fabric of space stretch faster with time. Inside a dense galaxy cluster, gravity fights back. It pulls matter together, resisting this expansion. But inside a void, gravity is weak. There is almost nothing to hold anything in place. So here, expansion dominates. Galaxies inside a void are being gently pushed away from everything else. Not through space, but with space. Over billions of years, this effect becomes profound. A galaxy in a void will see fewer and fewer neighbors. Distant clusters fade further away, their light stretched into longer wavelengths until it slips beyond detection. This is not science fiction. It is a prediction grounded in our best models of cosmology. A future where isolated galaxies become entire universes unto themselves, cut off, not by walls, but by distance. James Webb's observations offer a glimpse of this process already underway. The galaxies it detected show minimal interaction, their motion aligned with the slow outward flow of the void itself. Measurements of their redshift, the stretching of light toward longer wavelengths, confirm something remarkable. They are receding faster than similar galaxies in denser regions, not because they move faster on their own, but because the space between them expands more freely. And in this freedom comes isolation. Imagine a night sky where every distant galaxy has faded away. No clusters, no cosmic web, only your own galaxy, surrounded by darkness. In many ways, a deep void is already a preview of that future, a place where the universe begins to forget its own structure. And yet, within this growing silence, Webb detected something else. A subtle signal, not of motion, not of matter, but of temperature. A faint thermal imprint lingering in the emptiness. And it should not have been there. In the silence of a cosmic void, temperature becomes almost meaningless. There are no nearby stars to warm the darkness, no dense gas to hold heat. Only the faint afterglow of the cosmic microwave background, a whisper of radiation left over from the earliest moments of the universe. This background fills all of space with a nearly uniform temperature, just 2.7 degrees above absolute zero. In most regions, it is smooth, almost perfectly even, but not entirely. Tiny fluctuations exist, differences of mere millionths of a degree. These variations are the fingerprints of the universe's earliest structure. Inside a vast void, the expectation is simple. Less matter means less interaction. and so the background radiation should appear slightly colder. This is not speculation. It is a known effect called the integrated Sachs-Wolf effect. As photons of the cosmic background pass through large-scale structures, their energy shifts subtly. In dense regions, they gain and lose energy in near balance. But in expanding voids, something changes. They lose slightly more energy, emerging just a little colder. What James Webb detected was consistent with this effect. A faint, measurable dip in temperature aligned with the structure of the void. And yet, it was stronger than expected. Not wildly so, not enough to break our models, but enough to raise a quiet question. Are our measurements incomplete, or is the void more extreme than we understand? Because in these regions, where matter fades, where gravity weakens, and expansion takes control, even the smallest deviations become visible. There is no mystery signal, no broken transmission, no moment where the universe truly cuts the feed. Only this: when we look into the deepest emptiness, we are not witnessing absence. We are witnessing the limits of structure itself. A place where the laws of physics continue quietly, uninterrupted, unamplified, laid bare. And in that stillness, we begin to notice just how delicate the universe truly is. Not loud, not dramatic, but endlessly expanding into silence.